Well, hello friends, welcome back to OS Haxing. Today we're going to look at a exploitable kernel bug that was recently introduced, and we're going to use it to get a root shell. And actually we're going to need to use the new bug, but also an older bug that I found today. And together we'll be able to get a root shell. And let me show you the first bug, actually. So the first one is in the ptrace syscall. That was just yesterday that we added it, and I was looking through it a little bit closer, and I realized that in the handling of the ptpeek operation, this is for like reading the memory of the remote trace process. We are supposed to validate the output location here, which is where we will store the data that we read from the remote process. But as you can see here, this only calls validate right. It doesn't actually do anything with the result. So the code should actually look like this. And because of this missing validation, it's particularly bad because if we pass this validation check, then we use a SMAP disabler to turn off SMAP, which is the supervisor mode access prevention. Basically, this turns off all protections that we have against accessing stuff that we shouldn't be accessing. And then we just write to an arbitrary pointer, which is user space controlled. So it's really, really bad. It's an arbitrary kernel write, basically, with SMAP disabled. And the result here is memory that we read in the remote process, and the output is where we store it in the reading process. So I guess maybe we should start by just making a exploit for this. So we'll just call it haxx because it's a cool name. So we'll need ptrace and stdio and unistd. And then I guess we'll do something like just a fork so that we don't have to have two separate programs. And then this will be the child process. So first thing we'll do is we'll say ptrace me, and I guess we just do that, I think. And then this gives the parent process a chance to attach using ptrace. So basically we'll just do like this, right? Child process, and no particular parameters for that one. And then here, now that we have attached, then we can just go into a loop. We'll say something like parent attached to child sleeping. And I guess we can check that it works out. ptrace me. All right. And then what we have to do is, or let me error check here as well. In case we screw something up, then it's good if we can see what it looks like. Okay, so now we have attached to, here we have attached to the child. When this succeeds, so we'll say printf. Maybe we can even do this. Parent attached to child. Okay. And then what we need to do is we need to peek into the remote process. And if we look at the bug again, we can see that in ptpeek what we do is we do peak user data in the peer process. So the peer process is the remote process that we've attached to using ptrace, pt-attach. So peak user data will fetch 32 bits of data from the process memory of your child at this specific address in the child. So we need to pass it an address that's valid in the child, but since we just forked, it's pretty easy. We can just make a buffer, haxx buffer even, and we can put some, I guess we need ACK types for this. We can put something nasty in there, like CLI halt or whatever, or I don't know. We'll put something else like hello friends, like that. And the trick here is that now this pointer here is actually valid in both processes, right? Because they share the address space. So what we can do now is we want to pt peak in the remote process with this particular address, and the data is not relevant for peak, I think. So, well, actually, so you would think that this would be enough, but if you look at the API of ptrace, because the problem here is that, yeah, sure, we can peek at this location and everything, but what does that achieve? We're not doing an arbitrary kernel, right? And it actually, we need to take advantage of the way that the ptrace syscall is called from user space. So in ptrace, we have, this is the normal ptrace parameters, but for the peak syscall, we actually pass some additional parameters. For the peak operation, we pass it an address in the remote program and also an output address in the local program. And this thing here, we can't control it through the libc syscall wrapper that this is. And let's go here and look at that. Because in the ptrace wrapper in libc, it actually creates a peak parameter object in case the request type is peak, and then it sets it up custom like, and potentially passes it as the address member of the normal ptrace params. So this is all because of the ABI that we use for syscalls. We can only fit 3 registers in the syscall ABI, so because of that, we use these structs and pass them instead. So we have to actually construct these structs here, but it's not such a big deal. So syscall sc ptrace params, and then the way that we call it instead becomes syscall sc ptrace params. So now we just have to set everything up. So PID is going to be the remote PID, or our child PID. And then the address is going to be the address of our special peak parameters, peak params. And then we have the data, which is irrelevant, but we'll zero it out just because. And then we have pt peak. And, oh, I guess we should cast that actually. U8. All right. And peak params, we need an address. So this is the address in the remote program that we want to read. So that's our haxx buffer. And we'll just cast that to U32. And then we also need the out data. So this is the local pointer that we want to store to. That's how it's intended to be used, but this is the thing that's missing validation in the kernel. So we can actually write wherever we we damn please here. And let me show you what that would look like. So let's write to the base of the kernel memory space. And we have to cast that like that. Okay, so, oh, I guess I should do something with that. We'll say ptrace returned whatever we returned, and then return 0. Okay. ptrace returned 0. So that's pretty weird. Now let's try to write something somewhere. So this thing should have complained, right? So if we go into the kernel here and we actually add the validation, return efault. Then it would fail. So we get an efault error, and it doesn't let us write to that memory. Now, what can we do with this? So it turns out that now we can write wherever we want. So there's a million ways that you can exploit that. And I found a really, really nasty way that we can exploit it, because it turns out that the kernel image, like the executable of the kernel, is actually writable in memory as long as you're executing in kernel code. So what we can do is we can just grab the symbol table of the kernel, or actually let's go in disassembly here, and we'll get the getgid, is this called maybe? I like that one. So if we go to getgid here, and let's remove the validation again, just so we don't forget that. And then what we can do here is we can actually grab the address where getgid starts, and we can just put that here as the target address of the peak. And then now what's going to happen is we're going to copy the first 4 bytes of this string into the start of getgid. So we can actually do something a bit more interesting, like what are we gonna do? I guess CLI halt is pretty good. So this will like just hang the kernel basically. Or is it 5, 4? I always forget which one is which. Yeah, cli is fa. So yeah, turn off interrupts and then hang the kernel. And yeah, so let's try that. Okay. Right, so now we have overwritten, I think, the start bytes of the getgids is called, so we can test that by running id, which will try to get the group ID, and we hang. So that's pretty bad. User space overwriting kernel code. And it should be basically trivial to get a root shell if you can overwrite the kernel code. But just to follow through all the way, let's go to setuid, maybe it's the easiest. So in setuid, we do, first we check that you have the id promise, but it doesn't matter because we didn't pledge. And then we verify that either you're setuiding to a UID that you already have in your, that's fine for you to set UID to there, or if you are the super user. Otherwise we return eperm. But we can just patch these checks out, right? and then skip straight to this part. So here is the disassembly. So I guess these are probably the promise checks and required promise. Let's see. It expands to some debug output, yeah. So you can see this is the debug output, end of debug output, calling crash. If we don't have a promise, we crash here. But if we don't crash, then we go probably here, AB1D, let's see. Is that where we would jump to if everything is good? Yeah, so if everything is good, then we jump to AB1D, which is down here, AB1D. And that's where we do compare followed by another compare. And for all good, then we will store the specified UID in these two variables. So we can, if we just, the easiest maybe is to just patch here. Like this is where we jump to after the promise check succeeds. If we just pass a short jump, jumping over all of these guys and jumping straight to the assignments, that would be, so we want to jump from, let's bring up Python here. So we want to jump from this, and I have to cheat and look up how jump instructions are encoded. Show jump x86, please. Oh, here we are. Okay. So we want a jump short relative. Displacement is relative to the next instruction, and it's a 2-byte opcode, or a 2-byte instruction. So the displacement is relative to our current offset plus 2. So AB1D is the current offset, so it's plus 2. And then we want to jump to this mob here and 2B. Chicka chick. So the distance is 12 bytes. And it was EB is the opcode. So that's haxx0ring, just verifying. So it's, let's see, if we go to the haxx program, then we should store EB haxx0ring and then some nothings. And if we just patch that at the place right here, so instead of comparing and validating the UID, we'll just overwrite that code. And that should allow us to do a say UID. So say UID root. All right, and if that succeeds, we can just execute a shell. I think that should do it. It's really simple. Boom. So that's pretty bad. From user space to a root shell with these two bugs. So yeah, so just to recap what happened here, we spawn a child process, and then in the child process we say wait, using the ptrace call, wait for the parent to attach to me. And then in the parent, we attach to the child, and then we send this crafted request to peek, to retrieve some memory in the remote process in the child. But we tell it to put the output inside of the setUID function in the kernel, which the kernel happily does. So that's why we're able to call setUID, and it doesn't perform any validation. And then we get a root shell. So pretty bad bug. So let's fix this. And the first problem, we're going to add the validation, I think, first, or should we, like the fact that the kernel is writable, that's really bad. So maybe we should start with that. So the issue that I found is that when we boot up, what we do here in the boot code that runs before we enter into C++, we set up some initial page tables, and basically we organize it so that the lower 3 gigabytes of the address space are available to user space, and the top 1 gigabyte is kernel only. So it's an x86 operating system, so we have 4 gigabytes of address space. And basically it's organized so that in the top 3 gigs, the first 8 megabytes of those top 3 gigs are sort of pseudo-identity mapped so that they correspond to the lower 8 megabytes of physical memory as well. And we set that up lazily using, or it's not that we set it up lazily, but we set it up in a kind of a very casual way by just using, here we mentioned that we're using PS bits, which is page size bits. So we're using 2 megabyte pages, which is a convenient way that you can set up a page directory entry to refer to 2 megabytes of physical memory without allocating a separate page table. So because we've taken that convenient way here, then those 8 megabytes of memory in the bottom of the upper 1 gigabyte, they are all mapped as 2 megabyte pages. So it's just 4 entries in the page directory there. I think that's, I'm a little bit outdated, or like I haven't looked at page table stuff for quite some time, but I realized that we have this problem here. So because of this, and the reason that it's a problem, it's because when we boot up the memory manager code, what we do is we create a kernel page directory in C++, and then we read the memory map that we got from the bootloader, and then we set some things up, and then what we do here, we try to protect the kernel image, which is what it thinks it's doing, is it thinks it's disabling writing to the kernel text and read-only data segments. And furthermore, it tries to disable execution of kernel data and BSS. But this doesn't actually work because it relies on this ensure PTE function, which is ensure page table entry. So this is a function that will just give you back a mutable reference to a page table entry for a given virtual address. But this function assumes that you're not using 2 megabyte pages. It assumes that you are a normal page directory with 4 kilobyte pages. And nowhere in here is it aware of 2 megabyte pages. So this thing just goes and makes things writable, and then everything is still set to be using 2 megabyte pages, so none of this has any effect. And it actually overwrites some stuff that it shouldn't overwrite instead. So what we need to do is we need to switch to using 4 kilobyte pages, because the way that we protect the kernel, or the way that we want to protect the kernel, is we look at where the kernel text memory starts. So like, where does the code start and where does the data begin? So it's just a different way of saying, like, where does the text start, where does it end? If we look at our linker script, we can see that the text segment, we actually have start of kernel text, and then we have RO data, and then comes start of kernel data. So in between start of kernel data and start of kernel text, we have all of the text and all of the RO data. So it's a little bit confusing maybe, but that's why it's set up that way, so that we cover both text and RO data. And likewise for disabling execution of pages, we go from start of kernel data to end of kernel BSS. So it's from here to here, covering all of data and BSS. So what we got to do is we got to set up, because I don't want to do this in assembly. Like, we could change the boot code so that it switches to using 4 kilobyte pages instead of 2 megabyte pages, but then I have to write these loops in assembly, and I don't feel like doing that today. And actually, I'm gonna take this off because it's getting a bit warm. So we're just gonna make a new function here. Maybe we'll call it like set up. We'll do that actually before here. We'll do setup load pseudo identity mapping. Because the low identity mapping is mapping the bottom 1 megabyte of address space to the bottom 1 megabyte of physical memory. And for low pseudo identity, we're gonna map the 8 megabytes following the 3 gigabyte mark in virtual address space to the bottom 8 megabytes of physical address space. And we need to do that because the kernel image is always in the bottom 8 megabytes, somewhere in the bottom 8 megabytes is how it's currently set up. So, let's see, so we will add sudo. So now we're going to replace the page directory that the boot code set up. So we want to have, instead of those 4 2 megabyte page pointers, we're going to replace them with 4 actual page tables, and then we're going to have to populate those and fill in all of the individual page frame addresses. So let's see, I need some physical pages for this. So sudo identity mapping pages. I need 4 of them because 2 megabyte per page. So maybe we'll do this in a loop. Actually, it would be easier. And here we will allocate a supervisor physical page, and then we will it's going to contain page table entries. So page table is, we'll use quick map page. Okay, and then for an individual page table entry, it'll be at, we want to loop through all of them actually. So, and there are 512 page table entries since we're using PAE, physical address extension, so that we can actually have 64 bits of physical addresses. It's just that means that we need 64 bits per page table entry. So there's only 512 page table entries per page table. So we need that many, and then we'll just go like that. And for these guys, we're gonna have to say set, wait, you don't know what that is? Oh, because I didn't cast it. Page table entry. So we want to set physical page base to base plus j times page size, and the base will be I times 2 megabytes. Yeah. So basically, what we're setting up here is mapping from 3 gigabyte plus 0 megabyte. This is gonna be, let me write it out, virtual, physical. So actually, let me see. 3072, right? Maps to physical 0 megabyte. And then it just goes like this. This is what we're achieving by, by setting this up. So it's already set up this way, but it's using 2 megabyte pages and instead of using detailed page tables. And we need the detailed page tables to be able to turn off writability on a page granularity. If you're really familiar with this, then you know what I'm doing, but maybe it's a little bit messy if you're not familiar with x86 page tables. But anyway, we'll just push forward. So then we want to say, I mean, this are the default settings, so we'll just say writable true, present true, and execute disabled false, and user, we don't want user access, false. Okay. And then maybe when we are done with this, or I was thinking when we're done with this, we can flush all of it. But okay, no, I think this is okay. So now we've built up these page tables. Now we have to actually install them in the page directory. So in the kernel page directory, we have in the directory pages. So there are 4 directory pages that correspond to 0 gigabyte, 1 gigabyte, 2 gigabyte, and 3 gigabytes. So we'll grab the one for 3 gig, and it's a page directory, so we can actually map it using quick map PD. And we want to map wait, this isn't how that works. We just have to give it the page directory and the index, so 3 for 3 gig. And it's a star. Okay, so now we can go in here and say pd0 dot set page table base, and this is going to be the low pseudo identity mapping pages 0 dot physical address get. Yeah, so I think that's how we'll set it up. And once all of those are installed, then we can just flush entire TLB, and we'll be running with the new page tables. I think that'll work. And then this code here should just magically start working. Let's see if I did everything right. So the boot program only, the boot code only sets up 2 meg. mappings for per page protection to work, we need page granularity. That's why we have to switch to 4 KB pages here. Okay, I feel like that is a very hard to understand comment, so maybe we try that one more time. This code switches from 2 meg pages to 4 KB pages, switches the pseudo identity mapping, and wait, 8 first MB above 3 mark. Boot code sets it up as 2 meg mapping, 2 megabyte huge pages for convenience. But we need 4 kilobyte pages to be able to protect kernel. Okay. Oh, and actually we need to turn off the huge flag, because currently the way that it's set up before we come in here is that this doesn't exist, and these guys in the page directory, all of these entries have the huge, what does it say, huge? They have the huge flag on, and when the huge flag is on, then page table base doesn't point to a page table, but rather it points to a 2 megabyte contiguous range of memory that this page directory entry governs. And then you have only a 2 megabyte granularity of protection. So we'll turn off the huge state. I think if we don't turn that off, it's not going to work, because then it's still going to think that we want huge pages. And that doesn't work. Okay. So what are we doing wrong? I don't know. So we loop through these guys. We allocate 1 page. We do that here. Maybe we should print out what we're doing while we're doing it. So we'll say map virtual address space plus j times page size. That's not the virtual address. That's the physical address, and we want to say the virtual address is what is the virtual address? It's 3 gigabytes plus base plus j times page size. So quick map in use. Oh, wait a minute. That's what goes wrong? Oh, we never unquick map? Wait, why does that matter? Quick map PD, unquick map. All right. So why are we crashing? Quick map in use still. Oh, wait a minute. Quick map, we're quick mapping here. Not here, this one. The quick mapping code is a bit weird. So when we quick map something, we have to unquick map it because there's only one quick map page. So this is like a hack. If you have one physical page of memory and you want to map it into the kernel address space, you can use quick map. The only promise is you have to promise that you unquick map it when you're done. And if somebody else tries to quick map something while you're quick mapping, they're not going to get it. They're going to assert. So because we're not unquick mapping, then we are getting an assertion failure. And without that, it boots. Cool. And if we run our exploit now, segmentation violation. So I think, let's see, it's a error fault, unrecoverable page fault, write to address in the kernel. So that's really good. That means that the kernel is now write protected as intended. So that's a really good, if somewhat confusing change. But I think we can be happy with that one for now. So we'll say kernel. Switch the 8 megabyte, what do we call it? First 8 meg of upper 3 gigabyte pseudo mappings to 4K by pages. This memory range was set up using 2 megabyte pages by the code in boot.s. Because of that, the kernel image protection code didn't work since it assumed 4 kilobyte pages. We now switch to 4 kilobyte pages during memory manager initialization. This makes the kernel image protection code work correctly again. Okay, so great. But it's still really bad though that we can even trigger the bug, right? Because just because we can't write to the kernel image, it doesn't mean that we don't still have a kernel write primitive that allows us to write anywhere, or almost anywhere, because we could still write to the kernel stack or to kernel data or anywhere else that's writable. So we have to validate, of course. So let's go in ptrace and let's add that missing validation here. Or actually, it's annoying that even though we failed to validate, then it still would allow you to even write to kernel memory. So we should switch this to use copy from user, because then it will at least assert. So that would be a good start. So we'll say copy to that guy from result value. Can we just do that? Because I think if we do that, then this will start to assert instead, which would be an improvement. Yeah, okay, so now we have an assertion in the kernel. I think it's better to panic and assert in the kernel than it is to allow user space to do bad things. So getting rid of the SMAP disabler, very good. And there are a couple of other SMAP disablers in this file, so probably going to fix those as well. But right now we're just focusing on this particular piece of code. So we'll say, or yeah, let's just fix this one separately. Kernel, use copy from user in ptrace ptpeak. But I like the fact that you can even call this without doing something with the result is like, this is totally avoidable. So we can just mark this with no discard, which we should have done originally, because this makes it a compiler error to not do something with the result of this function. So we'll do that for all of the validate family here. And we'll see. Maybe something else breaks. And we can do a second video. Okay, so there's our ptrace failure. Yeah, so this is what we want, right? Like you have no discard, ignoring the return value of validate right, declared with no discard. And then we can go and fix it. So then not only are we fixing the problem now, but we're also making this exact bug a compiler error in the future. So that's really good. So kernel. Fix missing validation or ignored validation. Don't ignore validation result in ptrace ptpeak. Also make it an error to also mark all of the memory address validation functions no discard to turn this kind of bug into a compile error in the future. Yeah. So I think there we have it. Those are the fixes that we want to make. So let's look at how this code would run now. That we validate, we use copy from user, and what even happened here? And we protect the kernel from writing. So we have 3 mitigations in place, and you try to run this, and you just get operation not permitted. And this is an e-fault right here from ptrace. No root shell for you. So, cool. So we have been through the whole thing now. We found the bug, exploited it, got a root shell, and then fixed up the issues going backwards. Working our way through the issues from the lowest level to the higher level. Inside the kernel, I mean, from like the memory page tables up to the ptrace API. So I think that's pretty good, and that's basically the whole video. So thank you for watching, and I hope that you saw something interesting. I think this type of stuff is pretty interesting, and I know it's been a while since we did a haxxing video, but the moment I spotted this bug, I thought, you know what, let's just make a video about this, because it's fun to make these. Anyways, thanks for hanging out, and I'll see you next time. Bye.